To understand the physical scale of legacy 20th century rocketry, you have to look at the F-1. This is the engine that lifted the Saturn V to the moon. It was massive enough that you could park a Jeep inside its nozzle, and it produced an immense amount of thrust. By the time of the space shuttle, engineering had shifted towards extreme efficiency. The RS-25 engine was still physically massive, twice the size of a modern Raptor, but it produced about 190 metric tons of thrust. This chart plots engine footprint against thrust output to show exactly how these legacy systems compare to modern hardware. The F-1 sits high on the thrust scale, but takes up enormous area. The RS-25 and SpaceX's earlier Merlin engine fall much lower on the thrust axis. And then there is the Raptor 3. It creates 280 metric tons of thrust out of an incredibly compact 3-meter by 1.5-meter frame. To pack this much thrust into this much space, the engine must convert pressure more aggressively than any legacy design. Increasing thrust without increasing the hardware size is a problem of internal energy density. At a basic physical level, a rocket engine converts pressure into thrust. Propellants burn inside a chamber, releasing massive amounts of energy and expanding into high-pressure gas. Because matter naturally wants to flow to areas of lower pressure, that gas rapidly accelerates out the back of the nozzle, pushing the vehicle forward. Generating more thrust from a smaller engine means increasing that internal pressure. The latest version of the Raptor combustion chamber operates at 350 bar, or over 5,000 pounds per square inch. That is a sustained pressure load that would immediately crush a nuclear submarine. For comparison, SpaceX's older Falcon 9 Merlin engine runs at roughly 100 bar. Operating at these extremes makes efficiency a requirement rather than a luxury. Sustaining 350 bar means the engine cannot afford to waste energy, pushing SpaceX toward a more complex, integrated architecture. The baseline requirement for any liquid rocket engine is simple. You need to route liquid oxygen and liquid fuel from their storage tanks down into a central combustion chamber. But you run directly into a fluid dynamic constraint. Matter naturally flows from high pressure to low pressure. If the combustion chamber is running at an extreme 350 bar, your injection pressure must be higher than that. If it isn't, the reaction will flow backward into the fuel tanks and detonate the entire vehicle. To forcefully drive these liquids into a highly pressurized environment, rocket engineers use turbopumps. A traditional setup relies on a gas generator. This acts as a miniature rocket engine, siphoning a small amount of oxygen and fuel to spin a turbine. That turbine connects to a driveshaft, which powers the main pumps. In an open-cycle design, like the Merlin engine, the exhaust from that gas generator has already done its work spinning the turbine, so the system vents the excess exhaust overboard. Dumping that high-pressure exhaust outside the vehicle wastes potential energy. It caps the maximum efficiency of the engine, which severely limits your theoretical pressure maximums. To go higher, you have to transition to a closed-loop system. In a staged combustion closed-cycle engine, the exhaust from the gas generator isn't thrown away. Instead, that high-pressure gas is rerouted directly back into the main combustion chamber. But this creates a severe chemical problem if you are using traditional RP1 fuel, which is highly refined kerosene. Kerosene is a long-chain hydrocarbon. Because of its molecular structure, RP1 is very difficult to fully combust inside a small preburner. When it burns, it leaves behind a solid carbon byproduct. This causes coking.
Black soot rapidly accumulates inside the plumbing, clinging to the walls and destroying the delicate, high-speed turbopumps. You can safely vent that soot overboard in an open cycle, but if you try to hold all that pressure inside to build a closed-cycle reusable engine, standard 20th century aviation fuels make the mechanics impossible. This is exactly why the Raptor requires an entirely different propellant. SpaceX switched to deeply cryogenic liquid methane. Methane has a highly favorable 4-to-1 hydrogen-to-carbon ratio. It is extremely easy to fully combust, meaning it burns perfectly clean and leaves zero carbon residue behind inside the machinery. But liquid methane serves a dual purpose. Before it ever reaches a preburner, the deeply cryogenic liquid is routed through the outer walls of the engine nozzle. In a process called regenerative cooling, the cold methane absorbs the intense heat of the nozzle, preventing the metal from melting. Simultaneously, this extreme heat boils the liquid methane, preheating it into a gas for a much more energetic combustion. Removing the carbon byproduct and managing the thermal load through the nozzle walls allows the system to reach and maintain these unprecedented chamber pressures. That leads directly to the Raptor's final architecture, full-flow stage combustion. Instead of one shared turbopump, the system splits into two entirely independent units, each with its own preburner. On one side, you have an oxygen-rich loop. Almost all of the liquid oxygen is pushed through a preburner, mixed with a tiny fraction of methane, and ignited to spin the oxygen turbine. On the other side is the fuel-rich loop. The heated methane gas coming from the nozzle jacket burns with a tiny fraction of oxygen to spin the fuel turbine. Because both loops burn perfectly clean, without coking, 100% of the propellants flow straight through the turbines and directly into the main combustion chamber. Getting this to run requires an incredibly precise startup sequence. In fact, a single Raptor engine cannot start itself. It relies on external equipment on the launch mount to spin up the turbines before ignition. The propellants are ignited twice, first to drive the massive pumps, and then again to generate the actual thrust. This cycle extracts every possible ounce of energy from the fuel, representing the absolute limit of rocket engine plumbing. Because the main chamber operates at 350 bar, turbopumps must output 600 bar to successfully inject gases without causing a backflow explosion. They hit this target through a phase change inside dual preburners, rapidly vaporizing cold liquids into hot gases to drive pressure up. These high-pressure gases are forced together inside the main chamber. Perfectly synchronized injection ensures propellants detonate precisely, rather than tearing the engine block apart. Maintaining this highly volatile, tightly interdependent thermodynamic loop is difficult, but it's the sole reason Raptor achieves a power-to-weight ratio no other engine can match. The theoretical schematic becomes a physical reality when you look at the base of the Starship Super Heavy booster. SpaceX packs 33 of these uniquely compact engines into a single 9-meter diameter cluster. Every single one of them has to execute that delicate thermodynamic dance in perfect synchronization, or the rocket blows up. The early Merlin engine was the result of a mandate for simplicity and low cost. The Starship program necessitates a more complex path, sacrificing simplicity to achieve the performance required for a permanent presence in deep space. Building a permanent human presence on Mars cannot happen with safe legacy technology. It demands the radical reinvention and managed insanity of the Raptor engine.